Okay, correcting some things that I said here that were wrong. I'm not really confused about kinetic energy versus velocity, and force versus position versus acceleration versus time. I wrote things down carelessly though, and recognized it. So here we are. Okay, so here's your force, net force versus position. Your acceleration versus position can also be written this way. Now, acceleration versus position, not something we deal a lot with. It requires a little bit of a calculus trick because position's related to time by the velocity. And what you get when you look at the acceleration versus time graph, areas correspond to changes in velocity, and all that gets a little bit confusing, and we're not going to try to sort that out now. That's really something you sort out in a differential equations class. Okay, so you have net force versus position has this shape. The area beneath the net force versus position graph is the change in kinetic energy. So this area is your change in kinetic energy up to this time. Since the cart started with velocity 0, it started with 0 kinetic energy. So its kinetic energy at this time, at this position, is whatever the area under this graph tells you. We're going to do more with that when we analyze the lab that we do with the cart and the magnets. Okay, now the net force graph versus position drops below the axis here. And now you have negative change in kinetic energy because the generalized area here is negative since the region is below the position axis. So what you have here is a loss of potential energy, of kinetic energy. And when you get to the point where the area from here to that point, the green area, is equal to the area here, you see that your kinetic energy loss will have become equal to your kinetic energy gain. So if you started with 0 kinetic energy, you gain kinetic energy, you lose kinetic energy. When the gain and the loss are equal, your kinetic energy is back to 0 and you're stationary again. So here's a point where your loss equals previous gain, and this is where the car becomes stationary. Missing a word here. Okay, now on a graph then of kinetic energy versus position, see your kinetic energy is going to go up quickly and then kind of level off because this curve is high, but by the time you get down here it's low. So when the curve is high, it means you're picking up kinetic energy fast. When the curve is low, it means you're not picking up kinetic energy very fast. And of course, when your curve is down below the axis, you're losing kinetic energy. So at this point, the kinetic energy is equal to the area under the first part of the curve. Okay, on this line actually at this point here. So the curve is white here, indicating that you're above the axis. Your F net is positive. But then your F net becomes negative, and that's the green region, so I change the curve to green here. And the graph turns around, goes back down here. Now you can change a graph of kinetic energy versus position to a graph of velocity versus position. And you can change, knowing velocity versus position, you get velocity versus time. But it all gets pretty complicated. As I say, that's a better subject for a more advanced class. Okay. So, now this statement is just a statement of what the integral means. Kinetic energy is the integral net force with respect to position, which you should know from the homework you've had over the last couple of days. You have a regime here on this interval. Now I've had to indicate it down here, but on this interval, your magnetic force is greater than your frictional force. You're picking up velocity, you're picking up kinetic energy because your net force is in the direction of motion. Between here and here, much longer interval, your force of friction is greater than, in magnitude, than the magnetic force. Okay, so the force of friction dominates, and now you have a net force in this direction. It's going to sap your kinetic energy. Your kinetic energy is going to decrease.